Lesson or section 4.3, logarithmic functions. And I got to say, this is my most favorite section, or most favorite chapter for that matter. I love logarithms. I don't know why. One of my favorite mathematical topics, but 4.3 logarithmic functions. For those that have gone through 1010 recently, some of this should be a review. So we're going to talk about how to go back and forth between exponential form and logarithmic form, and then also how to evaluate a logarithm, and finally, graph a logarithmic function. So just going to do a little bit of background of and get us prepared for understanding logarithms a little bit better. So we talked in section 2.8 about inverses. So we just want to quickly review just some more familiar functions to us in terms of inverses. So if we have y equals x squared, for example, and I've modified the domain so that x is only greater than or equal to 0. And what that gives us is just the right side of the parabola. So this that I'm pointing at right here is the right side of the parabola y equals x squared with this restricted domain of x greater than or equal to 0. So y equals x squared. In order to find the inverse, remember we switched the place of x and y. And then to solve for y, we need to figure out what the inverse operation is. So y is being squared, and I think we all know that the inverse operation of squaring is square root. So every single operation in mathematics has an inverse operation that undoes it. So if I'm squaring something here, the inverse operation of that is to square root. And you can see here again, this is just as a quick review from lesson 2.8. Here I've got y equals x squared. This graph here is y equals the square root of x. These are inverse functions. And you can see that there are a reflection across this line, y equals x. Now, if I change the exponent here, y equals x to the third. That's this graph right here, y equals x to the third. And we don't need to restrict a domain on this. The reason I needed to restrict the domain of y equals x squared, if I didn't and I included the left side of the parabola, then I wouldn't have a one-to-one function, and that would make the inverse problematic. So I needed to restrict the domain of y equals x squared so it could be one-to-one, but y equals x cubed here, this is already one-to-one, so I can take its full domain. If I find the inverse of y equals x cubed, I have switched the place of x and y, and now I've got to figure out what the inverse operation of cubing a value. So if I got y cubed, the inverse operation of raising something to the third power is a third root, or a cube root. So here we have a square root, here we have a cube root. So you have all different kinds of roots. You have a cube root, you have square roots, you have fourth roots, depending on the exponent. And then you can see here, this graph is the graph of y equals the cube root of x, which is the inverse of y equals x cubed. So the point I'm trying to make is nth root, any power is going to have an inverse operation. So if the power is n, then there's an nth root. And again, what I'm trying to illustrate is any mathematical operation has an inverse or an opposite operation that undoes it. And that's helpful for graphing, that's helpful for finding the inverse, but it's also helpful for solving equations. Like we can use those inverse operations to solve equations. For example, if we have this equation here, x squared equals 5, in order to solve equations, we use inverse operations. That's basically what solving equations is using inverse operations to isolate a variable. If I want to get x by itself, I have to use the inverse operation, which is to square root both sides. And then I have x equals, in this case, plus or minus the square root of 5. And if we change the power to x cubed, then I can use a different root, because like I said, every operation has its own unique inverse operation that undoes it. So if it's raising to the third power, I would just do a third root. So then x equals the cube root of 11. But let's relate this now to exponentials. So in lesson 4.1, we talked about exponentials. f of x equals 2 to the x. You can see the graph here. There's no vertical shift up or down, and so the horizontal asymptote is the line y equals 0. I have my y-intercept at 0, 1, then a point 1, 2, and then a point 2, 4. Now this is f. This is the function f. The inverse of f, I'm going to switch the place of all the x's and y's of these 3 points. So 0, 1 becomes 1, 0. 1, 2 becomes 2, 1. And 2, 4 becomes 4, 2. And also notice that my horizontal asymptote at y equals 0 has become a vertical asymptote at the line x equals 0. Now this is the inverse of this function, but I'm not quite sure what the equation is going to look like yet. I know that the original function had an equation of 2 to the x. What is the inverse going to look like? Well, if we come down here, I've got y equals 2 to the x. The inverse is first switching the place of x and y. So I've got x equals 2 to the y. But now we need to figure out a mathematical operation here, because this operation needs to be undone. I need to get y by itself in order to write this inverse. But y is an exponent with a base of 2. And so at this point, there are a lot of students that suggest we'll use some kind of a root. The problem is with roots, going back up here, a root, or like a square root or a cube root, these roots are the inverse of exponents. So a root cancels an exponent. A cube root cancels a power of 3. A square root cancels a power of 2. Roots don't cancel bases, because what I need to do here is I need to cancel a base of 2 so that I can get y isolated. So what cancels a base? That's the question. What kind of mathematical operation can I perform on this so that I can cancel this 2 and get y by itself? And it's not a square root, it's not a cube, it's not any kind of root, because if I use some kind of a root, that means I'd be trying to cancel the exponent. That's not what I'm trying to do. I'm trying to cancel the base. And this is where logarithms come in. And this is the primary function of a logarithm, is to cancel bases. And we need that. One reason we need that is to be able to find inverses like this, to find the inverse of an exponential. Another reason we need this mathematical operation is to solve equations like this. So now, instead of x squared equals 5, now it's 2 to the x. And there is no such thing as an x root to try to cancel. There's no such thing as that. What we need to try to do to get this x by itself is somehow cancel that base of 2 so I can isolate x. And we're going to come back to both of these equations and to this inverse problem here in just a second. I'm just trying to first help all of us understand the need for logarithms and also the function. What is it that they do? The function of a logarithm is to cancel a base like this so that x, or whatever variable it is, can be isolated so we can solve equations. So here's a definition of a logarithm. And it's common for logarithms to be defined in conjunction with exponential equations. So if we start with an exponential equation, y equals b to the x, and again, to review some terminology, this is the base, b is the base, this is the exponent, this is the exponential term. Okay, so the exponential term has a base of b. This symbol means equal. This expression, or this equation, is equal to this equation. And you notice that this exponential term has a base of b. Logarithm also have a base. Logarithms have bases because there are multiple different kinds of logarithms, just like there are multiple, let me go back up here, just like there are multiple different kinds of roots. This is a square root that matches a power of 2. This is a cube root that matches a power of 3. It's the same idea as with logarithms. There are different logarithms that have different bases that are going to match up with the base of the exponential. what we need to talk about is the connection between these two equations and how to go back and forth between what this is called exponential form and what this is called logarithmic form. So first, let me show you how to undo or to go from this form to that form. So if I wanted to get this x by itself, the first thing I would do is try to cancel the base. Logarithms cancel bases, but you have to use the same logarithm, or you have to use a logarithm with the same base rather. It's the same base as this exponential. So if this has a base of b, then what you need to use is a logarithm with a base b. And since this is an equation, you do this to the other side as well. And a logarithm that has the same base as an exponential base is going to cancel each other out. So as long as the bases are the same, so this is a base b, this is a base b, as long as the bases are the same, a logarithm is going to cancel the base of the exponential, leaving the right side as just x. And x is no longer, this x here is no longer an exponent because the base is gone. So you don't need to write x as an exponent anymore. It's just a normal variable at this point. So this is how we went from exponential form to logarithmic form, which is what this is. Now reversing the process, if it's in logarithmic form and we want to go back to exponential form, we need to cancel the logarithm. So going back to a phrase I've said 3 or 4 times already, if you want to cancel a base, you use a logarithm. Well, if you want to cancel a logarithm, you use a base. And it has to be the same base as the base of your logarithm. Now, you have to be careful how you write this and show that you're using a base. If you write it like this and multiply it, that's not a base, that's multiplication. A base means that you have a base and an exponent. So if you're going to use a base to cancel the logarithm, you need to write b as the base, and then the logarithm is your exponent. And then since this is an equation, you have to do it to the other side. So you use a base of b, and now this is your exponent. And bases and logarithms are inverses of each other. So if you have a base of an exponential and then the logarithm that has the same base, those are going to cancel each other out. So this cancels that, leaving y equals b to the x. And that's how you go from logarithmic form to exponential form. Now, what I've just illustrated are some of the basic properties of logarithms. I've got 4 of them here. This logarithm has a base b. This expression here, b, is really b to the first power. And then remember, the primary function of logarithms is to cancel bases. So if you have a log base b and then an exponential with a base b, the bases are going to cancel, leaving the exponent, and that's why this is equal to 1. Now for property number 2, it's a very similar property, just extension really. This exponential has a base b. This logarithm has a base b. Since they have the same base, they're going to cancel each other out, leaving the variable. Now this one here is an interesting property. Log base b of 1 is equal to 0, and here's why. Log base b of 1 is equal to b to the 0 power, because remember, anything to the power of 0 is equal to 1. So you can replace 1 with b to the 0, and now you have log base b, and then an exponential expression with base b, leaving 0. That's why it's equal to 0. And then property 4 is what we just illustrated there up above, with going back and forth between logarithmic form and exponential form. If you have a logarithm, that's your exponent with a base b, and your exponential term has a base b, then those cancel each other out, leaving the expression inside the logarithm. So those are 4 basic properties we're going to use in all 3 of today's learning target, going from writing something in exponential form, writing something in logarithmic form, and evaluating logarithms. So our first learning target, well, actually, before we get to our first learning target, which is writing an exponential form, there's two special logarithms. One of them is called the common log, or common logarithm. And all it is a logarithm with a base 10. And the reason this is called the common log is our number system is a base 10 number system, meaning we have a 1 spot, a 10 spot, a 100th spot, and then with decimals we have a 10th spot, a 100th spot. So our number system is base 10, which means when we are solving mathematical equations, because we're a base 10 number system, quite often we have to use a logarithm with a base 10. And rather than writing log base 10, mathematicians, because this is used so often, just write this as log with no base. So anytime you see a logarithm with no base, just know it's log base 10. It's called the common logarithm. Another one that's very, very frequent, just as common actually as common logarithm, but it's called the natural logarithm. And natural because it uses the natural number, and all it is a logarithm with a base e. But you never see it written that way. You will always see it written ln. So all ln is, natural log, is really a normal logarithm, just has a base of e. So those are two special logarithms that sometimes get a little bit more attention. And incidentally, those are the only two logarithm functions on your calculator. Most calculators have a log button, which is a log base 10, and has a natural logarithm button, which is a log base e. Okay. So first learning target, writing an exponential form. And remember, this is what we practiced here, is if we have something in logarithmic form, we can write it in exponential form like this, doing exactly what we did here by using a base on both sides. So just to illustrate it one more time, here, if we have an expression like this that's in logarithmic form, first check the base of the logarithm, because you have to use the same base as the base of the logarithm. This has a base b. So in order to cancel this logarithm, we have to use a base of b and then a base of b on both sides, because a base is what cancels a logarithm. And now what we have left is y equals b to the x. And this is exponential form. So to practice, part A, log base 2 of 16 is equal to 4. We need to write this as an exponential term. So we need to cancel a log base 2. So since this logarithm has a base of 2, what we need to do is use a base of 2 on both sides. And a base 2 is going to cancel the logarithm, leaving 16 equals 2 to the 4th power. And just always double check that what you have is a statement that's true. 16 does equal 2 to the 4th power. Okay, part B, log base 5 of 25 is equal to 2. Same thing, we need to cancel now. This one has a log base 5, so we're going to use a log base 5 on both sides. Or sorry, we're going to just use a base of 5. Base of 5 here, and a base of 5 here. And make sure you're taking a mental note. This especially is not 5 times 2. This is 5 to the 2nd power. 5 is your base, 2 is your exponent. Okay, now here, the base of 5 and the log base 5 cancel, and you're left with 25 equals 5 squared. Okay. Part C. And I'm just showing you a lot of these so you can get exposure to all the different kinds of logarithms you're going to see, but it's really the same story every time. First you check to see what the base of the logarithm is, and then that's the exact base that you use on both sides to write it in exponential form. A base 3 cancels log base 3, so 1/27 is equal to 3 to the negative 3. Okay, part D, first you check the base of the logarithm, and since we just barely talked about this, hopefully remember that when you see a logarithm with no base, it is base 10. This is a common logarithm, so that's the base you're going to use. Base 10, base 10, a base 10 cancels a common log, so you have 1,000 equals 10 cubed. Now part E, this is natural log. And again, hopefully you remember, since we just barely talked about, natural log is really just an ordinary logarithm that has a base e. It's just not written. So this really has a base e. So this is what we're going to use on both sides, a base e, because a base e cancels a natural log. So you have x equals e to the third. Now the same technique could go in reverse, and that's what we do for our second learning target, is when we want to write something in logarithmic form. So what we need to do is undo this exponential term here. We have a base and an exponent. We need to undo this, or we need to separate this out so it's not an exponential term, which really means we need to cancel the base. And again, it is logarithms that cancel bases. So if I want to cancel this base, I'm going to use a logarithm that has the same base, so a log base b. And then same thing over here, log base b. So now that y is inside the logarithm function, and it becomes log base b of y. Y is inside that logarithm. It's kind of like it's inside of a square root. Y is inside of that logarithm. And now over here, the log and the base b cancel each other out, and you're left with x. And now that is logarithmic form. So that's what we're going to practice right here. We have 2 to the third power equals 8. That's exponential in form. So what we need to do is rewrite this in logarithmic form. So we need to undo this exponential term here, or this exponential expression, meaning we need to cancel this base. And we're always focusing on bases because we need to have a matching logarithm base. So we're going to use a logarithm with a base 2. Log base 2 cancels base 2 there, so we have 3 equals log base 2 of 8. And here part B, now we check this exponential has a base 4, so we're going to use a logarithm now with a base 4. So log with a base 4, and then over here logarithm with a base 4. Logarithm cancels a base 4, so we have negative 2 equals log base 4 1/16. And you can either write logarithms with parentheses like this, or you can use logarithms without parentheses. It doesn't really matter. Okay, part C, we have a base 10. Our exponential term has a base 10, so we need to use a logarithm with a base 10. Remember, that's just your common log, so you just need to write log with no base. That means log base 10. And then same thing here. Log cancels base 10, so we have 2 equals log 100. Okay, finally here, we have a base e as part of our exponential term. And so in order to undo this exponential, we need to cancel the base e. And remember, the logarithm that has a base e is called the natural log. So natural log cancels base e, so we're left with x equals natural log of 15. And again, I'm just going back and forth to show you it doesn't matter. You can do a logarithm with no parentheses, or you can do a logarithm with parentheses. So we've practiced this skill now. Going back up to earlier in our lesson, we talked about why do we need logarithms, what is the purpose, what's the function. One of the purposes was to help us find inverses. So if you remember here, we had f of x equals 2 to the x, and this is what we graphed in lesson 2.1. We talked about the inverse of f. The graph looked like this, and this actually is what the graph of a logarithm looks like, and we're going to see this here in a few minutes. We started finding an inverse, but all we knew how to do at that point was to switch the place of x and y. We didn't know how to do is get y by itself, because we had to cancel that base 2. We weren't quite ready for it, but now we know that in order to cancel the base 2, you have to do a log base 2. So those cancel. So log base 2 of x is equal to y. That's our inverse. So if we start with f of x equals 2 to the x, the inverse is log base 2 of x. So the inverse of 2 to the x is log base 2 of x. And then we can also use that same technique in order to solve, and we're kind of jumping ahead here. This is lesson 4.5, which is solving exponential and logarithmic equations, but these are just very, very basic. In order to solve this equation, we need to get x by itself. In order to get x by itself, I've got to get rid of that 2 as a base. The only way to get rid or to cancel a base is to use logarithms. So to solve this equation, we would use a log base 2 on both sides to cancel that. And so we have the solution x equals log base 2 of 5. We can do the same thing here, except now we're not going to use a log base 2 because this has a different base. If we have a base of 3, we just switch the logarithm to have a log base 3. And a log base 3 cancels a base of 3, giving us the solution x equals log base 3 of 11. So again, these are very simple and very basic exponential equations. We may be solving slightly more complicated ones in lesson 4.5, but this is essentially the idea, is that in order to solve exponential equations, you have to use a logarithm. And then vice versa, in order to solve a logarithmic equation, you have to use exponentials. So we'll see a lot more of that later on in lesson 4.5. Okay. So we've practiced going back and forth between logarithmic form and exponential form. The third learning target is evaluating a logarithm. Like this question here, what is log base 2 of 32? What is the value of this expression? And it's the same kind of question as, well, what's the square root of 16? Well, the square root of 16 is 4. Or what's the cube root of 27? Well, the cube root of 27 is 3. This is called evaluating a square root. This is called evaluating a cube root. So what we're doing here is evaluating a logarithm. What is the value of log base 2 of 32? And what we need to do is use properties of logarithms that we talked about a few minutes ago. Those 4 properties, somewhere here, right here. And mainly this one, we're going to use mainly property number 2 to evaluate a logarithm. And what we need to try to do is get a matching base to the base of the logarithm. So if you have a log base b, then this expression here needs to have a base of b. So what we do is rewrite. So 32 is a power of 2. It's 2 to the 5th power. So what you do is you rewrite the expression. Instead of writing it as 32, you write it as 2 to the 5th power. And now we can apply property 2, which says if you have a log with the same base as the base of your exponential, then those cancel, leaving the exponent. So log base 32 is equal to 5. And that's really all it is changing the expression inside the logarithm to match the base of the logarithm. So log base 2 of 8, we need to think about 8 as a power of 2. What power of 2 is 8? And the answer is, well, it's 2 to the 3rd power. So first thing you do is rewrite log base 2 of 2 cubed. 8 is the same as 2 cubed. And now since these have matching bases, log cancels the base, leaving the exponent. So log base 2 of 8 is equal to 3. So go ahead and try B and C. Go ahead and pause it and see if you can use that same technique to evaluate. So for part B, you think of 125 as a power of 5, and it's 5 to the 3rd power. So you'd rewrite it as log base 5 of 5 cubed, and now you can cancel the base using that logarithm. So log base 5 of 125 is equal to 3. Okay, part C is a little trickier. 1/16 is a power of 4, but you have to kind of think outside the box here. 4 raised to what power is equal to 1/16? So let me show you another way of thinking about what we're doing here. Let's suppose that we're getting into a little bit of trouble trying to figure out how to rewrite 1/16 as a power of 4. So here's something that I've seen some students do. We can assume that this is equal to something. I don't know what it's equal to, so I'm going to say it's equal to x. And now just rewrite it in exponential form rather than leaving it in logarithmic form. Write it in exponential form by using a base 4 on both sides to cancel the logarithm. So now you can write this as 1/16 equals 4 to a power of x. Quite often when students see it in exponential form like this, it's easier to visualize, I suppose, what the solution is. And this technique is called getting matching bases. If I can write this side to have the same base as this side, then the exponents are going to match. What I mean by that is 1/16 is the same as 4 to the negative 2. So 4 to the negative 2 is equal to 4 to the x. Now if 4 to the power of x is equal to 4 to the negative 2, then x is equal to negative 2. So we've just solved this equation like that. That's another way I've seen students approach these problems, is going out of logarithm form into exponential form. You don't have to do it this way. If we wanted to do this the way that we did in part A and B, it would be log base 4 and then rewriting 1/16 as just 4 to the negative 2, and then the log base 4 cancels the base 4, leaving negative 2. Now part D, this is common log. You notice this logarithm has no base, but it does. It's a base 10, and so what we need to do is rewrite 100 as a power of 10, and it's 10 squared. So the common log cancels base 10, giving us an answer of 2. Log base 7 of 49. Again, this one sometimes can cause some students to scratch their head a little bit. If we wanted to rewrite this, we'd have to rewrite not the base of the logarithm. We've got to write this as a power of 49. So 7 is 49 to what power? And that's what we need to think of. 49 to what power is equal to 7. And some students would recognize that the square root of 49 is equal to 7. So those are equivalent. And that's true. And then if you remember some of your properties of exponents from 1010, from Math 1010, the square root of 49 is the same thing as 49 to a power of 1/2. A square root and a power of 1/2 are the same thing. So now we have 7 is equivalent to 49 to the 1/2. So I haven't changed the numerical value of this problem. All I've done is rewritten it to have matching bases. And because they have matching bases, they're going to cancel out. Log base 49 cancels base 49, leaving 1/2. And again, the other way you could solve this problem, like I showed you in part C, and this is helpful for some students, is to think, well, I know this is equal to something. So let me erase this a little more. Log base 7 of 49. I know I can evaluate, I'm not sure what the value is, so I'm just going to say that it's equal to x, and then I'm going to use a base of 49 so that I can rewrite this in exponential form. So 7 equals 49 to the power of x. And then one technique to solve exponential equations is to get what are called matching bases. So I can change 49 into 7 squared. So it's 7 squared to the power of x. And then one of the properties of exponents that you talk about in Math 1010 is when you have a power raised to a power, you multiply. So then you can write this as 7 equals 7 to the 2x. Now we have this same situation. 7 to the first power is equal to 7 to the 2x power. This equal sign is powerful. It means that this side is exactly the same thing as this side. And since the bases are exactly the same, that means the exponents have to be exactly the same. or in other words, 1 has to equal 2x. So if you solve that, x equals 1/2. Get the same value as we got over there. Okay, last learning targets, graphing logarithms. Recall what we talked about earlier on in this lesson. We started with something from lesson 4.1, which was graphing exponential. So y equals 2 to the x. Remember, it has a horizontal asymptote at 0, a y-intercept at 0, 1, and then we plot a couple more points. This is the graph. We found the inverse a little bit earlier. Y equals 2 to the x. The inverse was y equals log base 2 of x. And all it is the inverse of this function here, y equals 2 to the x. So if an exponential function has a horizontal asymptote, logarithmic functions have a vertical asymptote at x equals 0. And I want to pause here for a second and talk about the significance of having a vertical asymptote. A vertical asymptote restricts the domain. So the domain of this logarithm function, the domain of this logarithmic function is 0 to infinity, not including 0. And this is significant, and it's an idea that's going to come up later on in section 4.5 when we solve logarithmic equations. And then tying this into the very last learning target, evaluating logarithms. You can evaluate log base 2 of positive values, like log base 2 of 4. That's equal to log base 2 of 2 squared, so it equals 2. You can evaluate logarithms at fractions, so log base 2 of 1/4 is equal to log base 2 of 2 to the negative 2, and so the bases are going to cancel, leaving negative 2. We can even evaluate log base 2 of 1, and this is one of the properties of logarithms we talked about near the beginning of this lesson. Anytime you have the log of 1, you can always change 1 into something to a power of 0. So since those bases match now, it's equal to 0. What we cannot do is evaluate this, log base 2 of 0. This is undefined, and here's the reason. Let's assume for a moment that this is true, that we can evaluate this. If this is indeed something we can evaluate, then we would say, well, this is equal to some value. Log base 2 of 0 is equal to something, so I'm going to call it x. If we rewrite this in exponential form, it's going to be 0 equals 2 to a power of x. This equation has no solution. There is no power of 2 that's going to equal 0. If I raise 2 to a positive number, 2 to the first power, 2 to the second power, I'm not going to get 0. If I raise 2 to the 0 power, I'm going to get 1. If I raise 2 to a negative power, like 2 to the negative 1, I'm going to get a fraction. 2 to the x is never going to equal 0. No solution. And another way we can think about this is the graph of 2 to the x, remember, look like this. This is the graph of 2 to the x. It never equals 0, because that's where your horizontal asymptote is. This has no solution, which means that this is undefined. So log base 2 of 0 is undefined, as is log base 2 of any negative value. So log base 2 of negative 4 is also undefined for the same reason. If I wanted to claim that this is equal to x, and I rewrote this in exponential form, y equals 2 to the x. 2 to the x is this graph right here, and every single value of 2 to the x is positive. It's all above the x-axis. There's nothing below the x-axis. So it's impossible to have negative values here. The point I'm trying to make is you cannot evaluate logarithms at 0 or at negative values. You can only evaluate logarithms at positive values greater than 0. And that's why the domain is from 0 to infinity. That's why we have a vertical asymptote at 0, which only allows us to use x values greater than 0, no negative values. So three things to graph a logarithm function. And it's really the same three steps as graphing exponential functions. Remember, to graph an exponential function, you find the horizontal asymptote, the y-intercept, and then you plot some more points. Well, for logarithm functions, you find the vertical asymptote, which is usually a 0 unless there's horizontal shifting. Then you find the x-intercept by letting y equal 0, and then you plot points. So, as an example, y equals log base 2 of x minus 1. Remember from section 2.6, we have a horizontal shift now. This is to the right 1 unit. The whole graph is going to shift to the right 1 unit, including the vertical asymptote. So the vertical asymptote that's usually at 0 is going to shift to the right 1 unit. So there's our vertical asymptote. The second step is to find the x-intercept, and remember we find the x-intercept by letting y equal 0. So if I want to find now that y-intercept, I have to create an equation. 0 equals log base 2 of x minus 1. And again, I'm asking you to jump a little bit ahead to section 4.5, which we haven't talked about yet, but this lesson 4.5 is entitled Solving Logarithmic Equations. The nice thing about it is we have the skills we need to solve a logarithmic equation. In order to solve a logarithmic equation, you simply need to cancel the logarithm. And we know what cancels a logarithm. It's a base. Bases cancel logarithms. So in order to cancel that logarithm, I have to use a base that matches the base of the logarithm. So I'm going to use a base 2 on both sides to cancel the logarithm. 2 to the 0 power there is 1. So 1 equals x minus 1. If you add 1 to both sides, you get x equals 2. So there is your x-intercept, 2, 0. Now we need to plot a few more points. And you can choose your x values, or you can actually, some students prefer to choose the y values. It really doesn't matter. I'm going to choose x values, but you need to be careful and choose x values wisely. What I mean by that is, even though you can use any x value to the right side of that vertical asymptote, you want to make sure that you use an x value that's going to end up giving you a power of 2, because we have a log base 2. For example, 3 is a good choice for x, and you're saying, well, 3 is not a power of 2, and you're right, but when you plug a 3 in for x and subtract 1, 3 minus 1 is 2, and 2 is a power of 2. So I'm going to use x equals 3 and evaluate log base 2 of 3 minus 1 is log base 2 of 2, and remember 2 has an exponent of 1, and now the bases are going to cancel, leaving 1. So 3, 1 is on my graph. The next value of x I'm going to choose to use is 5, and again you're saying, well, 5 isn't a power of 2, but when I plug 5 in and subtract 1, I get 4, and 4 is a power of 2. So log base 2 of 5 minus 1 is log base 2 of 4, which is log base 2 of 2 squared. Bases of 2 are going to cancel, leaving 2, so we have 5, 2. The domain is from 1 to infinity, not including 1. The range is all real numbers. Now this one, log base 3 of x plus 2. Notice there's no parenthesis. Here the parenthesis meant that the minus 1 was inside the logarithm function, and it's inside the function meaning it was a horizontal transformation. This plus 2 is not in a parenthesis with the x, which means that the plus 2 is not inside the function. This is the logarithm function. The plus 2 is outside of it, meaning this is a vertical transformation. So the +2 moves the whole graph up 2 units. Now, if a graph is just moving up or down, that's not going to affect the location of the vertical asymptote. So the vertical asymptote is still going to be at this line x equals 0. So there's the vertical asymptote. It has not moved left or right because this is a vertical shift, not a horizontal shift. So your vertical asymptote is there. Now to find your y-intercept, to find your x-intercept, you let y equal 0, which means we're going to create an equation 0 equals log base 3 x plus 2. The 0 equals log base 3 of x plus 2. Now we still are going to have to cancel a logarithm using a base, but that is always the last step of solving a logarithmic equation. You cannot cancel a logarithm if there are mathematical operations outside of the logarithm. So you got to cancel all of the mathematical operations outside of the logarithm before you can cancel the logarithm. So I would need to subtract 2. 0 minus 2 is negative 2. Now there are no more mathematical operations outside the logarithm, so now you can cancel the logarithm using a base 3. Base 3 cancels a logarithm. So x is equal to 3 to the negative 2, which is 1/9. So the x-intercept is 1/9. So if we have 1, 2, 3, 1/9 is really close to 0. Now you need to choose a couple more points for x. I'm going to choose x equals 1 because that's just going to give me log base 3 of 1 plus 2. And remember, anytime we evaluate the log of 1, that's equal to 0. So 0 plus 2 is 2, so 1 comma 2 is on the graph. Now since I have a log base 3, I want to choose values that are going to give me powers of 3. So 3, for example, is going to be log base 3 of 3 plus 2. This 3 right here has a power of 1, and then the logs are going to cancel because they have the same base. 1 plus 2 now is 3. So 3 comma 3. So the domain is from 0 to infinity, not including 0. And the range is all real numbers. So that finishes up our last learning target, graphing logarithms. Our third learning target was evaluating logarithms. Here, we evaluate logarithms by canceling the logarithm by getting a matching base. And then our second learning target was rewriting into logarithmic form. To rewrite in logarithmic form, remember, so part A, for example, 2 cubed equals 8. What we did is used a logarithm on both sides because logarithms cancel bases. So then we had 3 equals log base 2 of 8. Our first learning target was the opposite of that, which was writing in exponential form. So if we had like part A, log base 2 of 16 equals 4, to cancel a logarithm, use a base. So 16 equals 2 to the 4th. That's called exponential form. And that does it for lesson 4.3, logarithms.